This 2023 study details the development of an ethnoSTEAM e-module for fourth grade science. The researchers achieved an Aikens V score of 0.91, a very valid classification. Operational metrics support this, recording practicality scores of 87% from teachers and 88% from students. These results address a persistent gap in science education. Many conventional classrooms remain dominated by teacher-led explanations that restrict students to lower-order thinking skills, like simple recall and basic memorization. The researchers secured these outcomes by bypassing generic science examples. They engineered a three-stage pedagogical model that uses a specific piece of local cultural heritage to drive hard science acquisition. This approach is a direct response to Indonesia's Merdeka curriculum, a national education policy designed to replace dense material memorization with student-centered, contextual learning. This image of the Garuda Pancasila emblem represents the institutional core of that policy, the Pancasila Student Profile, or P5. This mandate requires schools to weave character education, global diversity, and local wisdom directly into daily instruction. This creates a strict constraint for curriculum developers. They must satisfy rigorous hard science standards while simultaneously meeting these mandatory cultural integration targets. To resolve this, the researchers deployed ethnoSTEAM. This pedagogical framework bridges the epistemological gap between indigenous community knowledge and formal scientific inquiry. ethnoSTEAM provides contextualized cognitive scaffolding. By treating cultural heritage as an empirical baseline, educators use it as an effective vehicle for teaching 21st century science. The first layer of this model tackles a specific academic standard, the physics of energy transformation. To anchor this concept, the curriculum utilizes a traditional agricultural artifact from the Yogyakarta region, the Talang Krasak water wheel. Rather than introducing fluid mechanics through abstract textbook diagrams, the module grounds the physics in a structure the students already recognized from their own environment. This animated diagram illustrates the core principle at work. A horizontal flow of water carries kinetic energy, which directly strikes the flat paddles of the wheel structure. That linear kinetic force is intercepted and converted into rotational dynamics, yielding usable mechanical energy. To prove this concept, the curriculum requires students to physically construct their own miniature replicas of the water wheel. As we see in this demonstration, manipulating the physical materials forces the learner to actively negotiate with the mechanics of the fluid flow. This process grounds the abstraction. The students verify through their own construction that STEM principles govern their immediate cultural surroundings. Once this physical baseline is established, the students possess the necessary foundation to transition from simple observation into active engineering. The Talang Krasak wheel successfully maps the theoretical equations of energy transfer onto a tangible, observable engineering challenge. The module manages this engineering challenge using project-based learning, or PJBL, as its primary structural engine. This flowchart maps the six-phase PJBL syntax used in the study, from an essential question through design and scheduling into monitoring, assessment, and evaluation. The critical pivot occurs in the fourth phase, where students transition theoretical designs into physical testing. The curriculum does not provide a flawless set of instructions. It is deliberately designed to induce mechanical friction and guarantee initial points of failure. During testing, students routinely encounter structural defects. Their replica wheel might stutter, misalign under water pressure, or fail to capture the kinetic force efficiently. When a design fails, the students are forced into a troubleshooting loop to isolate the cause of the inefficiency. They have to critically evaluate specific mechanical variables, testing to adjust the paddle angle, redistributing the weight of the frame, or reinforcing the central axis stability. This iterative cycle of testing and adjustment is the exact mechanism that develops higher-order cognitive skills and 21st century creative problem-solving. It mirrors the authentic engineering design constraints faced daily by professional STEM practitioners. This PJBL syntax creates a cycle of critical evaluation and mechanical calibration, requiring the same analytical rigor used by engineers to resolve real-world technical obstacles. The Yogyakarta ethnoSTEAM framework then deliberately extends this learning process beyond the physical boundaries of the laboratory. The module culminates in a school-wide Thazor, referred to as Market Day. During this event, students are required to publicly exhibit, explain, and economically position their engineered water wheel replicas. This activity serves a specific institutional function, tying directly back to fulfilling the national Panchakki student profile mandates. Specifically, Market Day is calibrated to target the development of entrepreneurial character and crucial interpersonal communication skills. The pedagogical mechanism relies on defense. Students must justify their creative and engineering decisions to peers, teachers, and potential customers walking through the bazaar. This defense process forces the students to clearly articulate the complex physics and engineering concepts they applied during the construction phase. Placing their product within an economic framing provides a layer of real-world validation for their scientific work, proving its utility outside of an academic test. For educators, this cross-disciplinary progression from physics to engineering to economics creates a highly robust and holistic assessment model. Market Day integrates technical skills into a social context, requiring students to demonstrate how scientific rigor supports the viability of a finished product. Looking at the discussion section of the Marianti study, we identify the root cause of those positive questionnaire responses. The researchers note the high practicality score is a direct result of enabling students to implement their knowledge, making learning instantly meaningful. The combination of ethnoscience, project-based learning, and entrepreneurship provides a multifaceted assessment of modern capabilities. Requiring the learners to operate simultaneously as physicists, engineers, and entrepreneurs creates deep, lasting cognitive resonance with the material. The module's high Aikens V validity score of 0.91 is the direct result of forcing students to operationalize their knowledge across these interconnected domains. The Talang Krasak water wheel module succeeds by layering cultural context, mechanical friction, and economic application. It proves a central philosophical point. Local cultural wisdom does not compromise scientific rigor. Instead, it serves as a highly effective vehicle for delivering it. For instructional designers and STEM curriculum developers globally, this case study offers significant implications. Almost any abstract STEM concept can be successfully grounded by identifying and reverse engineering a culturally relevant physical artifact. When culturally responsive education is structured around a rigorous engineering syntax, it directly drives the acquisition of hard science. The Yogyakarta ethnoSTEAM PJBL matrix offers a validated, replicable framework for integrating local wisdom into inquiry-based science instruction.